over the summer, Hannah and I have been working on special vehicle identification on HOV lanes with InvisionAI. Okay, we'll start by talking a bit about ourselves.
So yeah, I'm Hannah, and I'm a second-year master's student at Dalhousie University. My thesis focuses on music information retrieval using generative models, and I work under the supervision of Dr. Sagibor.
And for myself, I recently got a bachelor's degree in computer science from University of Toronto near the end of November 2022, and I was recently doing research with Jimmy Bach as part of on large language models as part of the Vector Institute. All right, so we'll start by talking a bit about our use case description, then go into our data set, methodology, experiments and results, and then end with future directions. So first, I'll start by talking a bit about who is InvisionAI. So InvisionAI, they enable edge devices such as remote cameras and sensors to interpret the world around them without relying on costly hardware or cloud connections. They provide real-world 3D situational awareness, including 3D detection, geolocalized tracking across sensors, and sensor fusion. And one of their projects is vehicle occupancy detection, or a VOD, where the idea here is given a vehicle to count the number of occupants or people within that vehicle. And this is useful for doing things like monitoring HOV lanes, where the number of people, like if there's a vehicle with a low occupancy, like one person, and that vehicle is traveling across an HOV lane, then that vehicle will be should be fined. They also have an autonomous rail project where the goal is to enhance railroad safety by detecting obstacles and hazards across varying weather conditions, right? Such as if there's a child like standing on the railroads. And they also have this interesting crowd view project where if you look at the image like right over there to my right, it's a 3D reconstruction of the NJ transit system. And using this reconstruction, it allows them to do things like track people flow and detect anomalies within the train station. They also have a similar project on Toronto's Yonge and College intersection, right, where they can do things like monitor people going across the crossroads on the intersections and also the flow of vehicles. All right, so let's talk a bit about our use case. So to understand our use case, you should probably start by understanding what HOV lanes are. So you guys have probably came across this and know about this already, but these are designated lanes that can only be used by vehicles that are carrying 2 or more people, and exemption rules can be applied to special vehicles. And the problem with this is that road operators have to sit there and manually monitor these HOV lanes to enforce exemptions or apply penalties to vehicles traveling on these lanes. And this is obviously very time-consuming and error-prone because it's being done manually. And we can automate this process using computer vision. So InvisionAI's solution is their current VOD system, which I talked about a bit earlier. And that system will currently count the number of people within a vehicle, but they don't have support currently for special vehicles, which should be exempted from the regular rules. So Hannah and I have been working this summer to apply, to extend the system to include special vehicles. And in doing this, it will make the lives of law enforcers easier. All right, so let's talk a bit about our data set. Right, so our data set consists of grayscale images of shape or size 1920 by 1080. And below, you can see 3 images of high quality, good images where it's easy to tell if this is a normal vehicle versus a special vehicle. And something interesting to note is that we actually, in our data set, we have multiple shots of the same vehicle. Like InvisionAI sensors will take a burst of images for the vehicle, which is useful for capturing different angles. And yeah, so let's talk a bit about our data now. Right, so our data set consists of roughly 125,000 labeled images from this place called Surrema, which is a location in France. And only like 2,600 of these images, so 2%, consisted of special vehicles, right? And what's more is that these 2,600 vehicles, we have multiple shots of the same vehicle. So in reality, there's only roughly 830 unique special vehicles if we eliminate those multiple shots like I talked about before. So this is not a lot for training a deep learning model. And what we know, and what Envision actually has a larger pool of 390,000 more unlabeled data. So Hannah and I have actually went through this larger pool of data and picked out samples of sirens and taxi signs. And in doing this, it was a lot of manual work, but we were able to enhance we were able to collect 8,500 more special vehicles. And so we went from roughly 2,600 special vehicles from before to 11,100, right? So we 4x the amount of special vehicles we initially had. And yeah, this is a lot more viable. All right, so now let's talk a bit more about some challenging samples for our model, right? So if you look at this first column on the right, my right, you'll notice that these images will have their rooftop cut off. And in this case, it would be difficult to detect if there's a taxi sign or a siren on the top of that vehicle. So it would be hard to see if that's a special vehicle or not. There are also some images that are very dark, as you can see in the middle column. And there's also these false negative cases where it's easy to confuse a special vehicle as a normal vehicle. So if you look at the very top image, right, that's actually a taxi car, right? And it's because there's a small white taxi sign at the top of that car, but it sort of looks like it's a part of the text on the truck that's behind it. So it could be easy for the model to sort of confuse that as part of the background. Okay, so we also apply some optimizations to our data set, such as we do downsampling, where the idea is how small can you shrink this image such that you can still pick out whether there's a taxi sign or a siren in this image. And this is useful because it will speed up training and inference and make it easier to export and share the data set with other people. We also do rooftop dropping, where the idea here is to place the attention of the image on the rooftop of the car, right? So that it'll make it easier for the model to pick out like a special object on top of that car. All right, so a bit about our methodology. So we train two different models. The first is a multi-class classifier, where our three classes are vehicle with taxi sign, vehicle with siren, and then non-special vehicle. But really, we only care about distinguishing between special vehicle and non-special vehicle. So we can combine those two classes of taxi sign and siren into a single class called special vehicle, right? And train a binary classifier instead. What are our evaluation metrics? So our two classes of interest are special vehicles and non-special vehicles. And from this, you can have like true positives, false positives, false negatives, and true negatives. And I'll talk shortly about why the false negative case is a lot worse than the false positive case, right? So with false positives, right, this is where a regular vehicle is predicted as a special vehicle. And in this case, it's not so bad because in InvisionAI's pipeline, they have humans that are sitting there and manually reviewing images that have been classified as special vehicles, right? So these misclassifications will eventually end up being caught by a human reviewer. Now, in the case of false negatives, this is where a special vehicle is misclassified as a normal vehicle. And because there are so many normal vehicles, like 98% of our data set consisted of normal vehicles, because it's infeasible for a human to manually review these cases, right? So in this case, what would happen is that a special vehicle with like a low occupancy, say one person, would end up being treated as a normal vehicle with one person. So that vehicle would end up being like fined rather than exempted. And that's not good behavior. And from those metrics, we can define the false positive rate, which is asking, out of all of the normal vehicles, what percentage of them have been misclassified as a special vehicle? And then we have the false negative rate, right, which is now asking, out of all the special vehicles, how many of them have been misclassified as a normal vehicle? And it would be more important to minimize this rate versus the previous one.
I think that's enough. Okay, so our end-to-end pipeline is pretty straightforward. First, as Brandon mentioned, because we have multiple shots for a specific vehicle, then we want to split the data into train, validation, and test. We want to ensure that all of the shots for a specific vehicle will be in same set. And then after we curated the data set and split it to train, validation, and test, the data goes to a pre-trained model, in our case, MobileNet. And instead of just fine-tuning the last layer of the model, which is the classification layer, we want to fine-tune the whole model because these models have been trained on completely different data set like ImageNet compared to our domain, and we want to fine-tune and update the parameters for the whole model like feature extractor and all the parameters. But we need to kind of limit the number of epochs that we have in order to not get overfit. And after the training has been done, we want to evaluate the final performance of the model on the test set. And now let's go for making some predictions. For making a prediction, we will send the images that we have to the model, and we have some labels for each of them. But at the end of the day, the only thing that matters to us, this is important, is that whether a specific vehicle is special or not, will be exempt or not. So we need to kind of fuse the information that we have from the model's prediction and move from image-level classification to vehicle-level classification. For example, in this image, we have 3 different shots for a specific vehicle, and only one of them will predicted as a special. So if we use a function like NP-any, or in another word, or function, if one of the prediction is a special, the vehicle will be labeled as a special. And we can play around with the fusion function that we have. We can increase the threshold from 1 to 2 or 3, or we can use max voting, and this will change the performance that we have. Okay, so we've done 4 experiments. So this is the experiment for binary classifier. These are the data statistics for the binary classifier. So the problem is kind of balanced. We have 11,000 samples for non-special cases and 11,000 samples for special cases. But the difference is that for the non-special case, all of the samples are unique vehicles. But for the special case, only 2,000 of the 11,000 are unique vehicles. And this has 2 benefits, actually. The first one is that when we have an unbalanced data set, one way to balance the data is to repeat the number of samples that we have. But because we have different shots, and these different shots have been captured from different angles, it helps the model to learn better the shape of the siren and taxi sign that we want to focus on. So this is like a data augmentation technique as well. And then 80% of the data goes to train, 10% to validation, and 10% to test. Okay, this is the loss curve for the model, for the low-res model and the crop model. For the low-res model, the model has been trained around 20 epochs, so the 20 epochs is enough for the model to converge. And for the crop model, after 10 epochs, the model tends to get overfit because the validation losses start to increasing. And yeah, the first hypothesis that we have is that the performance of the model on the crop data should be better than the low-res because the more focus is on the rooftop, which we want to look for the object of interest. But as you can see here, there is around 2% gap between the low-res model compared to crop model on the F-score measure. And this might have 2 reasons. The first one is that when we want to crop the data, when we want to crop the rooftop of the data based on the hyperparameter that we found, sometimes we might miss some of the objects that are at the end of the car. So sometimes we miss some of the sirens or taxi sign, which are at the end of the car. And this is like a contradiction for the model. So the model cannot see anything on the image, but the label is a special vehicle. So this is a room for confusion. And the other reason is that sometimes the shape and the model of the vehicle helps the model to learn. For example, if there is a truck and something is on the top of that, it should be predicted as siren. Or if this is like a normal vehicle, normal car, and there's something on the rooftop, there's an object on the rooftop, it will be predicted as taxi. So when the model loses this information, it's getting harder for the model to predict the special versus non-special cases. And this is a comparison between the confusion metrics before fusion and after fusion. So on the left side, this is like image level confusion metrics, and on the right side you have vehicle level confusion metrics. So in the left side, we lose 33 samples. So we mislabeled 33 special vehicles with non-special vehicles. And after doing the fusion and just narrowing the scope to vehicle level, there are only 4 vehicles that were misclassified. And again, this is the comparison between low-res data set and the crop data set. So as you can see, the false negative rate for the low-res data set is around 3%, and for the crop one after fusion is 1%. And the problem for the multi-class classifier is pretty much exactly the same, but the difference is that we have 3 classes. Again, the problem is balanced. We have 6,000 normal vehicles, 5,000 with siren, and 5,000 with taxi sign. And out of those 5,000, only 1,000 are unique vehicles. And 80% of the data goes to train, 10% to validation, and 10% to test. And this is the loss curve for the multi-class classifier. So as you can see, because the amount of data is less than the binary classifier, the model starts to get overfit sooner. So after 10 epochs, the validation loss for both models start to increase, and we should stop the training after 10 epochs. And again, we have the 2% gap for the F measure for low-res data and crop data. And if we play around with the hyperparameter a little, maybe the crop model can outperform the low-res model, but we haven't tried that yet. And again, this is the confusion matrix for low-res data set and the crop data set. So as you can see, the best performing model is the low-res data set on multi-class classifier, and the false positive rate is less than 1%, and the false negative rate is around 1%. So as you can see, there were 4 images for normal vehicles that the model predicted as a special compared to the crop data, which this amount increased by 18 number of images, 18 number of vehicles. And for the future direction, so the first easy way that we can go is to add another class for other exam vehicles like buses. So we can have like 4 class as taxis, ambulances, or vehicle with sirens, buses, and normal vehicles. The next one is to just use the license plate number for identifying special vehicles, because in most of the countries, these like license plate numbers have been registered for the special vehicles, and we can just look up into those databases. This is not a deep learning, but this is very accurate. And the next one is how to train a model to be more robust with respect to the shape and model of the vehicles, because, for example, the shape and the model of taxis are different between Europe and US, so we want to train a more robust model with respect to that. And the next one is how to automate the problem to have more project-dependent set of exemptions. And the last one, which is pretty important in our case, is that we need to clean the data set better, and we need to kind of clean the ground truth that we have. For example, in this image, this is an image of a driving a school car, which in our data set have been labeled as taxis. So we need to kind of clean the data, and if we want the model to distinguish between driving a school car and taxis, we need to collect more data and train the model one more time. Yes, this is our presentation.
Can you hear me? Okay, yeah, okay. So one of the questions I had when you were going through this was whether you guys know the baseline performance for, say, a human monitoring this type of thing, right? Like, do you know how well they perform in this task, generally speaking, if they were looking at the images?
I think the human performance should be pretty high, because identifying like siren and taxi sign in image for human is like pretty obvious. And then we went through the data, so we kind of labeled most of the data manually, and it was pretty fast for us. But because only 2% of the traffic is special vehicles, this is, in that case, is a little time consuming because you might lose most of the data because there's no special object in that. But yeah, it should be pretty fast for the human.
Yeah, I mean, presumably you might also run into an attention issue where like the person starts to stop paying attention properly. So the other question I had around that was if you guys did any sort or special treatments to your loss function, because I know you said you want to emphasize one particular error rate over the other. Did you make any changes, or was it the vanilla loss sort of sufficient for what you were trying to do?
It was like the vanilla loss. First of all, we wanted to like play around with the weight, so we wanted to add more weight to the special cases. But yeah, after like some hyperparameter tuning, we fixed it up.
I just have a quick question. Have you considered any errors where like normal cars have been classified as special cars? So maybe like a light diffraction like causes it to look like a sign to the model?
Actually, we do have some samples for that. For example, in this case, this is false positive, right? There is a motorcyclist behind the car, and the model gets confused with like taxi because it sees something on the rooftop, but this is not like a taxi sign. These are some samples that the model cannot capture very good, but yet most of the time, because the larger portion of the data are normal vehicles, most of the time the model makes mistakes. I mean, missing the special vehicle versus normal vehicles. But this is like one sample of the model.
Great, thanks.
When something is on the rooftop, the model cannot see that. It's just predicted as special.
Just one question on like comparison between the cropped and the low-res models. So you mentioned one hypothesis was the siren or the location of the siren would not be captured in the cropped image. But do you think there could be other reasons as well that the feature, basically the car image, which is not captured in the cropped image, if those features also contribute to, like indirectly contribute to identifying it as a special vehicle? So because in the cropped image, you're not including those features, right? So could that be a reason as well? Have you seen any samples around that?
Yeah, I think I've mentioned that. So most of the time, the shape of the vehicle helps the model to, the model or the shape helps the model to predict whether it's a special vehicle or not. And sometimes, yeah, I've seen some images that they're very like siren on the top, but the model couldn't capture that because it couldn't see the truck, the shape of the car, the shape of the vehicle. Yes, this is one that then the model lost the information from the shape. Like with the vehicle itself, you cannot capture it.
Yeah, basically it captured it well in the low-res case, but not in the crop. Understood. Okay, thanks.
I had a quick question, if I may. Am I allowed? My question was, given how little data you had regarding special vehicles, I'm assuming you also went through certain data augmentation techniques to enhance that data set. Would love to know more about that process, if that helped you improve your scores, your accuracy scores, and how it was like. Or copy pasting the siren signs on other pictures. So like, how did you work around having such little data set on special vehicles?